Csak nyugodtan.
Az IT oldalról rendben indítottuk.
Már elindult a videó streamen is.
Köszönjük.
Nyugodtan.
So, ladies and gentlemen, sorry for the late start. We had some problems with the arrival. There was more larger traffic jam as planned. But we are here finally, and the occasion of that we're here is that we are in a public defense of Ayham Aljawabrah, and the topic of his research is shiftability study and motion control of clutch. His supervisor is Dr. Aljawabrah from this department. My name is Professor Máté Zöldi. I am the chair of the Defense Committee. I am full professor here at the Technical University of Budapest. Our most important person after the presenter is the secretary, Mr. Dr. József Linka, who will manage all things and hopefully everything will be fine after his work. The pleasure is mine that we have two reviewers here, Dr. Károly Jálics from University of Miskolc, PhD degree, and László Kátai, PhD from Hungarian University of Agriculture and Life Sciences. The members of the committee is Dr. Ádám Báros, research fellow from Technical University of Budapest, PhD, and Ferenc Sarka, PhD degree from the University of Miskolc. As you were able to experience that we have an online streaming of the defense. It's not a hybrid defense, but we have a streaming, so if anybody feels that he's himself or herself disturbed, then please leave the room now. It's an opportunity. Yes, and at this stage, before the presentation, I would like to ask our secretary, Dr. József Linka, to present the candidate's academic CV.
Yes, thank you. So the PhD candidate, Ayham Aljawabrah, born in 1993 in Jordan. He is a PhD candidate at the Department of Railway Vehicles and Vehicle System Analysis at BME. Researcher in the field of vehicle system dynamics. He made his mechanical engineering BSc degree at Hashemite University in Jordan and his mechanical modeling engineering MSc degree here at the Budapest University of Technology and Economics, and did the PhD studies here in the Kandó Kálmán Doctoral School. Before his PhD studies, he worked as an automotive maintenance engineer internship at the Commercial and Industrial Corporation in Jordan in 2014 and mechanical design engineer at Professional Engineers TA in Jordan in 2015 and 2016. And in Hungary, he worked as a mechanical design engineer trainee at Innotech Magyar Kft. In 2022 and 2023. And now he works as a function software development engineer at Knorr Bremse R&D Center from 2023. He has comprehensive knowledge and extensive experience in softwares like MATLAB, Vector Tools, Atmos, SolidWorks, Creo, and has experience in Arduino programming. He had the Supreme Royal Scholarship for Bachelor Studies in Jordan and the Stipendium Hungaricum Scholarship for Master Studies and Doctoral Research in Hungary. The candidate speaks in Arabic, English, and Hungarian languages, and the candidate has published 10 articles, 2 of them in journals having impact factors 1.7 and 3.
Thank you very much for presenting the candidate's academic CV. And now the floor is yours. I kindly ask you to present your PhD results. And I think our wish would be if it can be not more long than 20 minutes, then it would be fantastic. But please, the 25 minutes is the maximum length that we can accept. So please try to keep it.
Hello everyone, thank you for attending my defense. I'm Ayham, I'm from Jordan, a PhD candidate at Railway Vehicle and Vehicle System Analysis under supervision of Mr. Aljawabrah. Today I'm going to present my scientific work related to the shiftability study and motion control of a doggy clutch. A doggy clutch, it's a kind of a gear shift element. The gear shift element is a necessary part in every vehicle transmission. Its role to synchronize the mismatch speed between the input side and the output side at the time of the gear shift. In the past, a kind of gear shift element have been developed called the synchronizer. In the left picture, the synchronizer have two parts: the gear which connected to the input side and the sliding sleeve that connected to the output side. And in the middle, there is a friction mechanism that reduces the speed difference between the input and the output side. However, this kind of synchronizer have some problems. Mainly, it has many parts, which include many backlash, and it makes very complex to model and control. Also, the friction mechanism reduces life of this clutch. Another kind that have been developed, which is called the doggy clutch, in the right picture, which is the same as the synchronizer, but the friction mechanism is removed. However, as there is no friction mechanism, there is a problem of the speed synchronization, which have to be solved. And after reviewing the literature, we found some several gaps, mainly related to the speed synchronization, also the phase impact during the gear shift, and also the complexity in the parametric study available to study the effect of the parameter included in the system. At the end, also we couldn't find that for the gear shift at high mismatch speed, that there is a gear shift algorithm or control system that guarantee a phase impact free gear shift process. So based on that, I aim to develop a criteria that can identify the gear shift process is a phase impact free or not. Also, I aim to develop in the literature. There is many parametric studies have been developed, like using finite element multi-body dynamics. Can I have just 30 seconds? I got some messages in Teams. I think there is a problem in the stream, if it's possible. Okay. So, having these complex parametric studies, I aim to develop a more robust method to study the effect of the parameter. Also, I aim to develop a control system that guarantees a phase impact free gear shift process. So for this one, I deal with the doggy clutch kinematics. First, I started to analyze the kinematics of the doggy clutch. As we mentioned, the doggy clutch have two parts, as seen in the left picture, the sliding sleeve that can rotate and slide axially, and the gear wheel that can only rotate. At the start of the shifting, as seen in this picture, there is an angular speed difference called mismatch speed, also an axial gap X0 and angular position difference called XP. The sliding sleeve starts to move until it covers the axial gap, as seen here. And then after it covers the axial gap, there is three possibilities. One possibility is case one that is continue moving without a phase impact. The second one, it can be blocked for some time and continue motion. And the third one, the third case, can be completely blocked. We are focusing on the case one. Once identify which case we will have, it's something we call the overlap distance that's shown here. It's the wheel in the teeth corner. So we assume if the sliding sleeve overlap the gear by this distance, so there will be no bounce back, and we have a phase impact free gear shift process. Based on this, and two assumptions that the axial speed and mismatch speed are constant during the real shift process, and kinematic analysis, we developed a criteria. We call it the shiftability condition, kinematical shiftability condition. So having the kinematical parameter and the geometry parameter of the double clutch, we can substitute them in this criteria and identify if it's successful, which is phase impact free, or unsuccessful, which include successful with the phase impact, or it will be completely free. We more generalize this for the chamfer tooth geometry, and for the chamfer tooth we have the chamfer angle, and also, unlike the flat tooth, the location of the overlap distance is not clearly defined. So we consider these three cases, three possible locations, and based on that, we calculated the modified backlash and overlap distance as seen in these equations, and substituted them on the shiftability condition that have been developed for the flat tooth. So also the chamfer angle effect will be included for the chamfer tooth geometry. Later on, I developed a parametric study to study the effect of many parameters included in the kinematical shiftability condition. And to summarize it, in the right we have the shiftability map, and we took two variables, x and y, and calculate the shiftability condition at each combination of these two values. The red value where it's unsuccessful, and the blue dot it's successful gear shift. Later on, I don't show this red dot for simplicity, and also I calculate some probability when some variables are uncertain. I performed this parametric study for the flat tooth geometry in some of the results, and for the chamfer tooth geometry, and this some of the results have been obtained. And here's some conclusion for what I did for thesis 1. And for thesis 1 summary, so I have developed a kinematical shiftability condition that guarantee a phase impact free gear shift process. Moreover, the developed shiftability condition include many parameters related to the double clutch geometry and kinematics. They greatly affect the double clutch shiftability. So I developed a method to study the effect of this parameter. For the second thesis point, I deal with the double clutch dynamic now. And here I aim to develop a full system dynamic that describes the dynamic behavior of the double clutch. The importance of this dynamic model serves as a foundation to design a motion controller for the sliding sleeve to control its motion. The double clutch system contains two main parts: the double clutch itself and its surrounding, it's mainly the gear shift actuator. We start with the double clutch. The same here, the engagement stages are similar from the kinetic point of view. However, here we consider the actuator force. Also, we consider the gearbox losses and the friction losses. So the mismatch speed and axial speed are not constant here. And also at the end of the free flight stage, in the second stage, there is a phase impact, and we model it here, and it's combined with a phase friction, which reduces the mismatch speed as seen here. After it passes second stage, there is the third stage with the side impact, and the side impact reduces the mismatch speed, which alternate around 0 until it reduces to 0. As seen here, we have three continuous states, which is the angular position of the sliding sleeve, and the angular position of the gear, as well as the axial position of the sliding sleeve, and these continuous states. However, as we see for each state, there is discrete dynamic. For example, for the second stage, we have only phase impact and phase friction. For the third stage, we have a side impact. So there's a discrete dynamic, but we have a continuous state. So we need a method to integrate this discrete dynamic in one dynamic model to be able to describe the continuous state time history. Here is something called the hybrid automata. It's a tool that enables us to integrate the discrete dynamic in one dynamic model. Each dynamic are modeled separately in separate blocklet state, as seen in the lower flow chart. So each dynamic model in L1, L2, 3, and L4, and the transition between these dynamics can happen along some specific paths, and each path is governed by a condition called G. So the transition can happen from one dynamic to another dynamic, and just when this condition is satisfied. And in this way, we can integrate the discrete dynamic in one dynamic model. I have modeled and simulated this model in Simulink, and here is some of the results. And for the gear shift adapter, we have an electromechanical gear shift mechanism. It's a desktop cam follower mechanism. It's convert the rotational motion to linear motion. The linear motion is provided by these two forces, and it's coupled to the doggy clutch, which can move axially. The rotational motion is provided by an electric motor. So this system has three parts: the mechanical rotational part, mechanical linear part, and the electrical part. The dynamic of each part have been modeled, and all the dynamics of these parts integrated together. And then we have this final non-linear dynamic model for the gear shift mechanism. I have modeled and simulated this model in Simulink separately, and also I integrated it with the doggy clutch dynamic model to have a full dynamic system model, and also it has been simulated to verify the model. And as a conclusion for the second thesis point, I have developed a control-oriented full system dynamic model. It's integrated from two subsystems, the doggy clutch dynamic and the electromechanical gear shift actuator. For the thesis point, I deal with something called the dynamical shiftability condition. For the kinetical shiftability condition in thesis one, I consider the mismatch speed and axial speed are constant. However, in some cases, the gearbox losses are present. Also, we consider the actuator force. So the axial speed and the mismatch speed cannot be considered, and we should consider the time history. So the dynamic here is common. So I aim to develop a more generalized condition to take the effect of the dynamic, gearbox losses and the actuator force. And I developed a condition called the dynamical shiftability condition. It's the same procedure have been developed for the kinetical shiftability condition, but based on the dynamics developed on the second thesis point. After dynamic analysis, we have this dynamical shiftability condition. I use the parametric study developed in thesis one to study the effect of this parameter. For kinetical shiftability condition, we had only this parameter. But for the dynamical shiftability condition, we had the extra parameter in blue, and here's some of the results. So as a conclusion for the fourth thesis point, for the third thesis point, based on the kinetical shiftability condition in thesis one, I developed the dynamical shiftability condition where the axial and mismatch speed are not considered constant through the re-engagement process. After I analyzed the kinematic dynamics, finally I aim to develop a motion control for the system. So for this point, I deal with the motion control of the doggy clutch, mainly the sliding sleeve. But here the goal to develop a control system that guarantee a phase impact-free gear shift process. Firstly, I need a reference signal for the position reference signal for the sliding sleeve that based on that, if it follow it, we can say we have a phase impact-free gear shift process. If we have the initial angular position, mismatch speed, and the geometry parameter for the doggy clutch, based on the kinetical shiftability condition, we can choose an axial speed value that guarantee a phase impact-free gear shift process. And based on that, this speed we can generate a reference position signal. However, in reality, the controller can't fully follow the requested reference signal. So we still don't guarantee that we can have a phase impact-free gear shift process. Now, rather than having just a single value for the axial speed, we took a range for the axial speed. And we substituted this range on the ax shiftability condition, and we have this middle figure. And we found that there is a continuous band with a value of 1, which means that shiftability condition is satisfied. We took this longest band, and we took the lower speed value at the lower speed limit, and the higher speed value at the higher speed limit, and the middle speed, that our speed that we needed to generate a reference signal. So the reference signal that we need now is the dashed black line, and the actual response is the green line. So we can say if the actual response from the controller is between the blue and red line at the impact position, XC0, the horizontal dashed black line, we can have a phase impact of free gear shift process. Moreover, I calculated the portion of this range for the axial speed where the condition is satisfied divided by the whole axial speed range. And I did this at different mismatches, different initial relative position value and mismatch speed. And we found for each mismatch speed, as the middle figure shows, that there is an initial relative position that if we start the gear shift at it, we have the highest portion for this portion for the successful area from the axial speed range that we choose. So before we have only the axial speed as a control variable, but now we have the initial relative position as a control variable. So at time 0, if we have a gear shift, we don't start the gear shift only when for a given mismatch speed it is at the optimal initial relative position as the upper curve shows. And based on that, I developed a complete gear shift algorithm shown in the lower left figure. And here is the architecture for the full system with the controller and the planet. And to control the motion, I have mainly used an LQR controller type. I integrated the developed gear shift algorithm and the design controller with the full system dynamics and simulated the system for different gear shift cases, and here are some of the results. So as a conclusion for the fourth thesis point, I have developed a control for the gear shift actuator and identified the optimal gear shift parameter depending on the Dopey clutch geometry. Here are some of the future works, and here are my list of publication. Thank you for your attention.
Thank you very much for your presentation and as well for keeping the time. And now the stage is for the reviewers. And in alphabetical order, I would like to ask first Dr. Karol Jalic to present his review.
Mr. Chairman, thank you very much for the work. I prepared a review, several pages, which is divided in 3 sections. The first, general remarks. The second part is dealing with the actual work of the candidate, and the third chapter is dealing with my opinion about the work of the candidate. So basically, I would like to read only the first and the last chapter of the review. I don't like to bore you with my 6 pages, 7 pages interpretation of the work. So we shorten the time of the review. So first of all, my general remarks are the following. The selection of the topic is up to date and important. shiftable gearbox is an essential component of a motor vehicle equipped with internal combustion engine. Due to its operational limits between idle speed and maximum speed. Even electrified vehicles can accommodate shiftable gearbox too, since maintaining the optimal consumption of electric motor has become also an important issue. As part of a shiftable gearbox, the synchronizer performs an important role by connecting the gear with its shaft. Many variants of the synchronizer are existing. One of them is the dog clutch. Dog clutch synchronizers are often used in gearboxes of motorcycles. This type was investigated by the candidate in his PhD work. The candidate's work and results are discussed in 7 chapters of total 83 numbered pages. In addition, there are the appendices 1 and 2 with additional 8 pages. The candidate summarizes the new scientific results of the dissertation in 4 theses. Based on the detailed table of contents, list of figures, list of tables, and nomenclature, it is easy to navigate between topics, chapters, and subsections. And the structure of the dissertation shows a thorough systematic working method, which also gives the dissertation scientific character. The candidate performed thorough literature research based on 100 literature sources. This ensures that the candidate has started in the right direction before starting the actual research work, or he was able to correctly answer questions that arose during the work. This is also proven by the total of 9 publications on this topic according to NTMPP. From a formal point of view, the thesis has a nice and professional design, as it should be. The graphical material is sophisticated, the values shown on the axis of the diagrams are easy to read. The text seems linguistically and grammatically correct. And I jump now to the last part. I already had the possibility to review the candidate's work for the home defense. In my previous review, I already suggested a lot of issues to be modified or completed. For example, the following modifications were performed. The end of the chapter 1 moved to the beginning of chapter 2, so this chapter was enhanced compared to the original text at the home defense. I find this is an appropriate modification. In chapter 4 and 5, the description of the simulation environment and the addition of conclusions and evaluation of the results were also added. In my point of view, it's not in the text, it's my personal note now. It was the main, let's say, weakness of the original version, and it was corrected. In chapter 6, the experimental investigation in the previous version was also modified. I originally suggested to complete the experimental work or delete the chapter. Candidate kept the text, he simplified it and moved it to subchapter 6.2 as possible outlook. I find this solution an acceptable compromise. In my current review, I can state now that all the required modifications, competitions were implemented by the candidate. Respectively, all other major and minor inconsistencies were eliminated. So, in my opinion, the PhD work is now more than complete. And next, chapter 6 presents the scientific thesis of the work. General can be stated. For T1, in my opinion, the formulation of the thesis is too long. Nevertheless, this thesis is accepted as it is as new scientific result. And the same is valid for 2, 3, and 4. Thesis 2, 3, and 4. The discharge work overall is excellent work. Thank you very much.
Thank you very much for your review. May I ask if you have any questions to the candidate?
Yes. I'm going to look for it in my papers. So I supplied 2 questions to the candidate. The first question is, by not considering the dynamic shiftability condition, what kind of negative effects in terms of noise and vibration phenomena can be expected? And the second question was, what strategies can be employed to optimize computational resource usage and simplify the algorithm at the hybrid automata model by still ensuring accurate and reliable performance?
Okay, thank you very much. As I guess you received most questions,
Yes.
I propose to, as the next step, to hear another review, and if we have all the reviewer questions, then I ask the candidate to respond to all the questions, if it's fine with you.
Sure.
And I ask now Dr. László Kátai to please show us your review.
Thank you. I consider that we are not in alphabetical order because consider the first or the last name order is the same. So I'm on the second. I also try to shorten a little bit my review, not to read all the points and all the sentences. First, a few remarks on the structural aspects. The scope meets the requirements of the doctoral school and, of course, doctoral PhD thesis work. And as it was mentioned, it has funded literature references which can show that really the literature review and the study of the literature is quite long and precise. And I also like to mention that I also had the opportunity to review the workshop version, and my opinion is the same, that the thesis has been much improved on several points, and it's now really very nice thesis work. What I would like to add that it really has much improved the ratio, but I had a criticism, introduction and literature review, but I still find the introduction a little bit too long. And particular merit of the thesis is the typically very high quality of the figures and tables, and that we can see in the presentation as well. The dissertation deals with an interesting scientific problem, shiftability conditions of droplet from kinematical and dynamical aspects. The overall thesis is not only interesting from academic or scientific point of view, but also from actual automotive industry, so from practical point of view. The first chapter, as I mentioned, the introduction would be shorter and would sufficient to present the relevance of the topic, highlighting the justification of the research area, and no need to go back to the history of internal combustion engine, for example. Chapter 2 is dealing with the overview of dot latches, which is really a good chapter and has a nice summary of that construction. Chapter 3 describes in detail the basic principles of movement and connection of the dot latch. It defines the necessary connections precisely and accurately. In table 3.1, my question is that why RPM is given in brackets, and we also could see RPM values in the presentation, why it is the omega value, which is angular velocity, and to change these parameters, you can pose a kind of problem in simulation as far the omega value should be in radian per second. Chapter, one more remark or question related to that chapter, that in 3.2. The effects in that paragraph, the effects of the parameters under study are analyzed in detail in nicely presented chapter. In real situations, several parameters can change at the same time, and how could you analyze this? That is one small question. Chapter 4 focuses to the dynamic behavior of the duck watch. It defines the necessary connections precisely and accurately again. And we can see really nice diagrams, easy to understand them. One additional question, that in figure 4.3, why the delta omega curve is linear between T1 and T2 time interval. In case of equation 55, the meaning of that should be defined in order to make it more clear for the public. And in 4.1.4, your reason for explanation why to choose K and D parameters to overlap the system. In figure 4.12, analyzing the overall situation, what is the real situation in practice or in the model? Do you know any data of the real happening case? Chapter 5, after analyzing the kinematic and dynamic behavior of the clutch, this chapter focusing on gear shift control. The chapter can lead to the practical application of the results. So I appreciate that it deals with it in sufficient detail. For the analysis, the candidate uses certain data set. What is the source of that? Control design and system simulation is a nice job, and explanation even in detail and in a correct version. And finally, chapter 6, new scientific results or thesis points. Here we can see 4 new scientific results. My opinion is the same, that in the dissertation, the thesis points are presented in a very long form. It was very nice to see here in the presentation that it can be summarized practically in one sentence. So one scientific results can be summarized in one sentence. And just to make a summary, I can accept all the 4 presented new scientific results or theses. I formulated 2 additional or separate questions. The first is based on the statement made at the end of chapter 3.2.1, which deals with the chamfer angle. What recommendation would you make for the value and design of the chamfer angle? And the second question, in the dynamic model, if the system is not overdamped or underdamped, does it affect the usability of your model? Of course, I had a statement that the thesis work I propose for public debate. As we are here, it's very clear that yes, my answer. Thank you.
Thank you very much to both of you for your hard work and your comments. And now the floor will be yours. I have to respond to the questions and comments of the reviewers. So please.
I would like to thank the reviewer for this for their nice comment and valuable question. They assist me a lot in improving my work and better to show it for the readers. And so I'll start with Dr. Yarich. I received, as you mentioned, 2 questions from him. The first question, what will the effect if we don't consider the dynamic suitability condition rather, but the kinetical suitability condition? Before I answer this question and how this relates to the noise and vibration, the noise and vibration usually it's measured at the complete powertrain level. So this includes the control of the engine speed, disengage the clutch, perform the gear shift, engage the clutch, and during all of these stages, the jet can be, or the noise can be measured for the gear shift process. However, in our case and in other many studies that have been done in the past that focusing only in the gear shift process for the inside the clutch itself, we deal with this from the point of disengaging a clutch, and we perform the gear shift, but we don't deal with the engage of the clutch again. So for the noise and vibration in the powertrain itself level, we didn't calculate it because it's outside of our work focus. However, as mentioned, the dynamical shiftability conditions have been developed to overcome some limitations. That for the kinematical shiftability condition, we consider the axial speed is constant. Also, the mismatch speed is constant, but in some cases, maybe the gearbox losses are present, and they can reduce the mismatch speed actually for the gear shift process. And if we choose an axial speed at the start of the gear shift process, based on the initial mismatch speed at the start of the gear shift process, later on it will not be the same value. So the chosen axial speed to guarantee a phase impact free, it will not be correct value because the mismatch speed is different and maybe it will be an impact free. For sure it will be some noise and vibration on the gear shift actuator level due to the bounces back of the sliding steel. And here are the references that I cited for my response. And for the second question, how can I simplify and optimize the computation for the hybrid automata model? Firstly, for the modeling technique for the dynamic system, there was the continuous time and the hybrid automata technique. For the continuous time modeling, all the discrete dynamics are modeled inside one dynamic block, and each dynamic is enabled based on a condition. However, at the same time, all dynamics are calculated. But in the hybrid automata model, the conditions are always calculated, but only the necessary dynamic is used. So the hybrid automata itself, it's a simplified strategy for dynamic system modeling. However, the optimization can be done in the modeling and simulation level based on the software. For example, in MATLAB, this hybrid automata can be translated to the state flow language actually, and how the user uses this technique to model itself, it can optimize the computation time of the simulation. And this was my response for the question for Dr. Yelch. And I will respond for Dr. Laszlo question. So, for the first question, why the RBM and rad per second have been used? The reason for that, actually, inside the simulation, it was easier, and as common, it's the SI unit, the rad per second, it's the common unit in the simulation. However, to better show the results and to better interpret them, after I got the result, I converted the rad per second to RBM to better show the result. So the rad per second, it was the main unit that used in the simulation, but RBM, it was between a bracket because I used that to interpret the result as seen in this figure. And for regarding the parametric study that I studied many different configurations regarding the Docker clutch geometry. In real situation, how can we manage this? Actually, in real situation, it's not possible to study all of this configuration. Since we have many parameters and different ranges, something called the Taguchi method or design of experiment shall be used. So we can study the needed possibilities. Moreover, if we have different geometries, we should have different doggy clutch should be manufactured and tested. Also, should be a test rig that can allow to install and uninstall different doggy clutches. And unfortunately, in the current situation, we don't have this test rig. However, the parametric study can serve as a guide to choose the doggy clutch geometry available or appropriate for the system. And the strength of this, as we've seen in my work, I could relate the doggy clutch kinematics, which based on the doggy clutch geometry and other parameters, to the motion control. So the parametric study serves as a guide. And the third question, the second stage, why the mismatch speed curve is linear during this stage. Actually, during this stage, it can be any shape, linear or non-linear. But I put this mainly firstly for the representation that represent during this stage due to phase friction between the teeth, there is a reduction in mismatch speed. The second reason, the model that I used during the simulation to simplify the simulation, it was a linear friction model. And regarding the overdamp and underdamp system, the first question was, in the real situation, if we know the real case, unfortunately, we couldn't test this on the test rig. So for the real situation, we don't know the real case, if it's underdamped or overdamped. However, I chose the K and D value based on other previous work. Mainly it's Gabriel Boca. He was working in similar field many years ago, and he used an overdamp system. And also we use this, it's called a spring damper model. We use this like inside the dynamic model or simulation to represent a wall. So I choose this K and D value based on Boca work. However, also I simulated this model. My model that I developed can be used for both cases, overdamp and underdamp. And we saw this in figure 4.12a and c, when I simulated the system for overdamp case and underdamp case. However, later on, I stuck with the overdamp case due to the motion control design. The underdamp case actually is more appropriate to design a controller, and the simulation will be faster in this case. Also, the actual response from the controller, it can be seen. And regarding what's the recommendation for the chamfer angle, if we should use a chamfer tooth geometry or a flat tooth geometry. Before I answer this question, maybe in other cases the chamfer it can assist. For example, in the synchronizer, actually the chamfer assists in the engagement between the teeth during the friction to reduce the mismatch speed. But there is a phase impact. Our work focuses on a phase impact free gear shift process. And based on our result from the parametric study, we see that as the chamfer angle increase, the blue area which represent the successful engagement area decreases. Also, the engagement probability as the chamfer angle increases also decreases, mainly for this figure. So what I concluded that for our case, for the phase impact free gear shift process, the chamfer angle has a negative effect in the system itself. So it's better to use a flat tooth geometry rather than the chamfer tooth geometry. And I hope I answered on both of your questions, and this was my response.
Yes, thank you very much for the answers. It's my role to ask the reviewers if they can accept the answers of the candidates. So please.
From my side, I accept your answers to my question. Thank you very much.
I also accept, yes, the answers.
Okay, thank you very much. So we seem to be on the right track now. And I asked our secretary to come up with our defense committee questions, and meanwhile I asked all other members of this defense to think over if you have any comments or questions to the candidate, or after responding to our question, that will be the last opportunity to challenge him.
Yeah, so the committee questions for the candidate. Please highlight the novelty of your research compared to previous works, for example, compared to work of Dr. Gergely Boka. And another question, in a design process, how could you implement your findings in a serial product? And I give it to you if you want to see it.
So for the first question, how my work have new scientific finding compared to Gergely Boka work. Firstly, for Dr. Gergely Boka, he considered the dopey clutch engagement at low mismatch speed. So something like below 10 rad per second, something very low. Sorry, 5 rad per second. Secondly, inside his work to reduce the mismatch speed, he used an extra component. It's called the counter shaft arch brake. So it was used in the input side to reduce the speed of the input side to make it comparable to the output side. Thirdly, for his work also, there is an impact between the teeth. So even if it does not, the sliding sleeve does not move in high speed, there is an impact actually between the teeth. And based on these 3 points, my work have been based. Firstly, I considered gear shift process at high mismatch speed, so it can reach 200 RPM. Secondly, in some cases like motorcycle, the counter shaft brake can't be used, this extra component. So my work have been done, so we don't need this extra component. While we can have phase impact free gear shift process. And based on this, in regarding Dr. Gergely Boka, there can be an impact between the teeth, but also in my work we try to guarantee a phase impact free gear shift process. So there will be no phase impact. And regarding how this work can be implemented in serial products, it's an interesting question. Actually, we are working in R&D center with chlorobremza, and we are testing this work, but we are still in the development phase with chlorobremza. It can be developed, can be used in the serial product, but it needs a lot of development. So this work is still in the development phase currently, and the main challenges to implement it in the serial product, there is many certain parameters for a given transmission, and also to design a good motion control for the given dynamic system. So once these challenges have been overcome, it can be implemented in the serial products. So this can be used, actually this work for the motorcycle in the software, transmission software for the motorcycle. Also it can be used in the electric vehicle. In the electric vehicles, actually currently they use the same kind of the dopey clutch, but they use the electric motor to synchronize the speed difference during the gear shift process. And many literature that I have been checked, there are many phases during the gear shift in electric vehicles that have multiple gear sets. And the longest phase is the synchronization phase, to synchronize the speed of the input side to the output side. And this kind of transmission is called clutchless automated manual transmission. So even there is no master clutch to disengage the input from the transmission. And actually, I have explained this in one of my paper. It's a long explanation that there is a possibility based on this work, it can reduce this, if this work, if it used, the synchronization is can be reduced as well. Thank you for your question. So this is my answer for your question.
Thank you very much for your detailed answer. I try to get in eye contact with the members if we can accept it. By my guess is that we are accepting the answers. So thank you very much. We accept both your answers. And now the opportunity is yours. First, if you have any questions or comments in the group.
From the committee side.
For the
Can I start?
take a seat.
So you developed in your second thesis a hybrid model of the dynamical system of the dog in your course chapter of your thesis. And of course it's a challenge for the motion control design and controller design. And you solved it very well by choosing a nominal hybrid mode and designing an L2 linear quadratic controller regulator for it. And my question is, did it cause any limitation in your control performance? And if yes, what development can be made to get rid of these limitations?
So what I could understand from your question that how the hybrid automata modeling could challenge the controller design?
Yes.
And the dynamic system modeling. For the hybrid automata itself, actually, it didn't have any challenges, even though it helped me more to verify my system because there are different stages. And in the beginning, I used the continuous time and I had many problems, and I didn't know from where they come. Then I shifted to the hybrid automata. However, for the hybrid automata, it helped me, but I had a problem in the dynamic model. It's for the electromechanical gear shift actuator. As we saw, it's a nonlinear model, actually. In the QR, it's kind for linear system control. But for some play around, like we can linearize the system. And if I can go back to the dynamic system itself. So in the equation there are this nonlinear bar and also this nonlinear bar. When I studied the system, I saw that this bar does not have too much effect on the dynamic response when I omitted or included it. However, this bar that have more effect, and we call it the time varying inertia because it's more or like it's an inertia. And during so this part is related to the axial position or the angular position of the disk, and I plotted the curve. And to make it more simple, to overcome this challenge, I took some, let's say, nominal value in specific places to design the controller based on this. And for the LQR, I had different set of parameters to control the system. So it's more like, it's not against schedule PID, but let's say against schedule LQR.
Yes, exactly. For example, in the future, working scheduling controller can be also evaluated and designed. But what benefits could it give? Thank you.
Is there any further questions or comments? I don't see any. Please.
It should be only a remark, namely that this dissertation this has now is already the third one in the life of our department, dealing with different aspects of gear shifting. The first one was the dissertation of Mr. Lower, carried out in an international environment. The second one, the work of Mr. Boca, which was mentioned before, and now the third one, which I have heard now. As the different technical tools, namely the automatization possibilities and electronic influences, had proposed, given only new questions, which should be good answered by the previous expired ones. Thank you.
Thank you very much.
Just, if possible, just one more, just for using a bit of time, one remark. The last question of the jury was, how can we use this work in the industrial practice? The goal was, maybe the colleague mentioned, but maybe I didn't pay attention. So the goal was to hold here with this mathematical tool, a modeling tool, we can do two things. Either we get an existing gearbox layout, existing geometry of Doct's clutch, and we can say if the available control tool, the actuator, is good enough for smooth shifting or not. This is a quite simple answer that you can give. Or if we have just the actuator tool, we can design the Doct's geometry in such a way that this given actuator can be fine for the shifting. This is what further development, not too much, can provide to this tool.
Thank you very much for this clarification. I don't know if you as a supervisor would like to say.
As a supervisor, just some words.
I think we are at the end of the open
So,
minutes.
Mr. Aljawabrah arrived here some years ago from the Faculty of Mechanical Engineering, where he was dealing with energetics. So this topic as gearbox and shiftability was a completely new topic for him, both from the practical side, gears, dog clutches, oil parts, and also for the control parts. So what I see as supervisor, he made a quite impressive achievement during these years, both in the understanding of the technical side of the things, meaning shafts, gears, ductings, and whatsoever, and also in the control side, understanding the new control tools, applying it and programming it. And also in the beginning of the testing of manufacturing, we had also some skills of programming these algorithms in practice. So I'm really satisfied with his work. Thank you very much.
Thank you very much. Then I think at this stage, I will close the open session, and we as committee, we go back and have a closed session, and hopefully very soon we will come back here.